Okay, 5.7. We're doing inverse trig functions, okay? So our objectives, we're going to evaluate the inverse for sine and cosine. Okay, approximate it for trig functions on a calculator. That's why I want you to have one. Compose trig functions and inverse trig functions. Apply the inverse stuff, and then we'll go ahead and do the other trig functions as well. Okay, so that's our objectives for today. Quick question. Let's see how much you remember. Do these two graphs, let's look at the first one. Does this have an inverse? That parabola?
No.
It does not. Yeah, it fails the horizontal line test, right? Okay, horizontal line test tells you if it has an inverse. This is a function, but not a function that's one-to-one. So if you remember from algebra, we had to restrict the domain to make it an inverse. Okay, over here, does this have an inverse?
Yes.
Yeah, passes the HL test. So if you remember, the reason why that's so important, I'll just draw a small little picture here. Okay, so if I had some number here gets mapped over to some number in the range, right? Well, if you think about it, if you have, okay, oh, didn't want to draw it that way. There we go. If I have two inputs that give me the same output, inverses go backwards. They allow you to figure out what x value gave me this. Well, if I have two of them, which one do I pick, right? So again, we have to restrict the domain to avoid that kind of situation. And we're going to do that with trig today, okay? We know that trig is periodic, right? It just keeps recycling. For sine and cosine, it's like every 2 pi, and you see those values over and over again. So we're going to have to restrict some things to make them have inverses. So here we go. Okay. So if I were to give you something like this, okay, and I want you to solve for the angle this time. Okay, we never had to really solve for an angle like this. So I would look at this and say, okay, that's your opposite, that's my hypotenuse. So I'd say sine of theta is 7/11. So now my next step is, how do I undo sine, right? To where the angle just gets by itself. If you think about normal algebra, if you had something like 2x equals 4, to get x by itself, you did the inverse operation. You divide it by 2. So I got to figure out what's the inverse of this guy, right? How do I get rid of sine to where theta is by itself, okay? So that's the problem we're going to be approaching here. So we have to find the inverse of sine to solve for theta, okay, to solve for that angle, okay? Now, so let's talk about just inverses in general right now. So inverses. Okay, so this is like a recall segment. So if you remember, the horizontal line test can help determine if a function is one-to-one and has an inverse. Okay, and we did that with the warm-up, right? We looked at these two functions, we drew a horizontal line, figure out if it has it. Okay, graphically, a point, which we'll call AB, on the graph of function f, we'll just use f, okay, corresponds to the point BA on its inverse function. Okay, so if you remember, inverses graphically, they just switch the ordered pairs. Okay? And then the last little detail for inverses, and then we'll go back to what it relates to sine. So the last little fact that we talked about in the past, the graphs for f and inverse of f are symmetric to the line y equals x. Okay? So it almost looks like a reflection of some sort. So I'll give you a small little picture underneath it. Okay? So if I had, here's my line. Okay? And let's say from here to here, this is my function f. Well, the other function, the inverse function, is going to go in the reverse direction. There's f inverse. Okay? So they're symmetrical on that line, y equals x. And we can do that with all of our trig graphs. I'll graph some stuff so you can see it visually as well. Not every single one, that'll take some time, but at least the first couple so you can see it. Okay, so now we established the inverse information. Now let's take a look at sine. Okay. Now what I'm going to do is I'm going to graph two periods, okay, negative and positive so we can see the full thing. I'm gonna use green. Actually, take that back. I'll use red, but I'm gonna need green for something else. Yeah. Here. I'll step out of the way here. There we go. So there is our sine wave. Okay. Notice that that does not pass the HL test. That horizontal line is going to cut through many places, right? So technically we would say sine doesn't have an inverse, but I want it to. Because again, if I go back to this problem, how am I going to solve it if it doesn't have an inverse? So we're going to restrict the domain just a little bit to where the HL test will pass, okay? But when we restrict the domain, we want to be careful. We want to make sure we get all the output values that it could have. So for sine, the output values go between what, 1 and -1, right? So can I chunk off a section of graph that passes the HL test and it still goes through 1 to -1 all of its values? And yes, we certainly can do that. So what I'm going to do is I'm going to section it off here and here. Okay? So I'm going to put this in green. So this part of the graph is what I'm going to use as my inverse of sine. Okay, so that's my domain restriction for it. Notice what's in green passes the HL test. It also includes all my output values from -1 to 1, which is good. Okay, I don't want to pick a section that only covers half of the output values. That's not good. Okay, so there we go. We're just segmenting. So let's go ahead and graph it. So I'm going to go ahead and graph the inverse now. So over here, I'm going to graph the inverse of sine. Okay. Just so we can see it a little bit clearer so we don't have like all the rest of the stuff. Now, graphing the inverse, if you remember what I said over here, is that the points switch, right? The XY switches. So I'm going to switch the XY axes to graph this, okay? So here we go. We'll have 1 here, I'm sorry, -1 and 1 here. Again, just flipping things. And then we'll have pi/2, -pi/2. We'll plot our 2 points. So pi/2 will be at 1, -1 will be negative pi/2, and then we will graph what that looks like, which is really cool. So that's what the inverse of sine would look like. So it's that green section here. All I did is I took it and just rotated 90 so you can see what it looks like. But there it is. That's going to be my inverse, which I'll use to solve problems like this now. Okay. So any questions on how I restrict that domain to make sure all the outputs are good? Okay. So underneath here, let's put a definition. So the inverse sine function, or we can call it arc sine. So I don't know if you've ever seen that before in other math classes, but arc sine is the same thing as the inverse for the sine function. And we have a symbol for it, which you might recognize from geometry. So denoted by sine with the -1 as like an exponent, okay? So if you see that, they're talking about the inverse of sine. Or we can write it like this, arc and then sine, using the abbreviation for it, sine, okay? So those are the, let me underline it. So these two right here is the two ways you can write inverse of sine, okay? Those are your two symbols, two labels there. So this is the inverse of the, now I'm going to use the word restricted sine function. Okay, because we did restrict it. Look at what I drew up there in the green. Okay, we're not looking at everything with that sine wave, just that part of it. So that's why we're calling it the restricted sine function. And we did it for the following values: -pi/2 to pi/2. Okay, so you can see right here, -pi/2. Pi/2 is where I restricted this. Okay. All right. So before I finish some basic facts about it, any questions what I did this one? All right. Let's keep going. So therefore, okay. So I can write my inverse as this. So y equals sine of -1x. So that's what I would put here. That's what the graph would be. So why not? Since we wrote that down, I can finally write what that looks like. So that's this, and then over here is just y equals sine of x. Okay. Now, this also implies, okay, if I just took this and flipped it, that's what this is here. So you could see this, but not technically. Again, this implies this. The double arrow just means that they're equivalent to each other. And I can do the same thing with arc sine. So, oops, arc sine of x is the same thing as sine of y equals x. Because remember, inverse is you're swapping out the x and y. So those are equivalent to each other. Okay? So all this is true where our x values are between 1 and -1, and my output values are between -pi/2 and pi/2, including those. Okay? So let me put this in green. So this is our domain and range for the inverse. So we're swapping things out. So in other words, when you approach this, think about like what angle gives me that output is what we're trying to figure out now. Okay? All right. Any questions? Let's try some examples. So let's find the exact values or state the expression is undefined. Okay, because that can happen. So I got 3 little examples here. So I will say computation-wise, this isn't difficult. What makes this lesson a little bit difficult is remembering the domain and range restrictions that we have here. Okay, that's really the key part that we have to keep in mind when approaching these. So the first thing I want to look at is this. okay? Looking at this guy, what I'm trying to do is I'm trying to figure out, I'll put this in green. So if I rewrite this as y equals the inverse of sine square root of 3 over 2. Okay, so I'm trying to figure out what's y going to be equal to. Okay, when I plug that in the calculator, what's it going to spit out? Okay. All right, so thinking about it, where do we see square root of 3 over 2? What angle do we have that for sine? What do you think?
30.
No, 30.
No.
60. Yep, that's okay. So pi over 3, right? Okay. So this is going to be equal to pi over 3. Okay. Now notice something. Is pi over 3 within my range out here? Yeah, so I'm good to go. So for this guy, okay, so y in this case is good, not approximately. Don't know why I did that. It is equal to pi over 3. Okay. So in other words, what we're trying to figure out is what angle gives me that output value. Okay. So let me just, I'll write it fully here. So we could say sine inverse of square root of 3 over 2 equals pi over 3. So there's my answer for that guy. Okay. Next one. Okay. I wrote this differently. Instead of writing it with the -1 exponent, I wrote it with arc, but they imply the same thing. So underneath it, I'll just rewrite it. So this is the same thing as me writing sine. Y equals the inverse of sine of -1/2. Okay. Now, we have to think what angle, when I take sine of that angle, I get -1/2. And we have to keep in mind that we're within this range here to do that. Okay? So we know that pi over 6 gives me 1/2, right? Okay, we know that. But because it's negative, we're going in the fourth quadrant route. So we're looking at not pi over 6, but a negative pi over 6 is what this is going to spit out. Okay? So if you want to put this, I'll put a little small note. We know that pi over 6 gives us 1/2. We do know that. But because it's negative, and because I'm trying to keep within my restriction here, which is the first and fourth quadrants, I know I'm looking at negative pi over 6 to get -1/2. So therefore, we could say this is equal to negative pi over 6. Okay. Now your calculator, some probably do. They'll give you the decimal version of that negative pi over 6. They won't actually spit out negative pi over 6. Okay. Last one. So for this guy, we're trying to figure out what y value, when I type 2.5 into the inverse of sine, what's the output going to give me? Okay. We got to be careful with this one. So 2.5 is my input value. Well, my input values can only go from -1 to 1. So no solution. This one's undefined. Okay? It will not work. So let me write that as a note. Since our x values are between -1 and 1, 2.5 does not work. So let's go ahead and just put here that this would be undefined. Okay, so no bueno for that one. Any questions on that? So again, it just, when I put a box there, that is very critical when it comes to these problems. Okay, so let's do the same thing for cosine and tangent. We're going to restrict them just like this. Then we'll list them in a table, all their characteristics, and then we'll try some examples out with them. So I'm going to go ahead and put her on this board right here. So I'll put here now, we can define the inverse cosine and tangent functions And I'll put in a similar way. Okay. So let me go ahead, I'll draw both graphs here. Okay, so there's cosine. Now I'll put tangent beneath it. Okay. Takes a little bit of time to graph this. By now, hopefully you know what the general gist of those graphs look like. We've been doing graphing for quite some time, so those should be kind of routine to just do that in your head, what the periods are, what they look like, and so forth. Now, for tangent, I did graph a couple periods just to kind of make some emphasis on some of these inverse stuff. So looking at cosine, again, I'm going to try to make sure that I get all the range of y values, okay, and making sure it passes the HL test. So I can see that if I were to cut cosine here and here, if I cut at those two spots, notice that this section of graph covers all the outputs, okay, which is what I want, and it's going to pass the horizontal line test. So that's going to be my inverse here. So on this side, I'll put the inverse graph. I'm not going to draw the other graphs. I think up to here we're good. We kind of know what's happening. But for the first three, I want to show you a visual as to why we're doing this. So here's the, oops, wrong color, the inverse cosine graph. Okay, so it looks like this. And notice that my range for there, we're going from like 0 to pi, okay? So that's going to be my domain for this guy, just between those values. Okay, now for tangent, well, again, if I were to draw a horizontal line, that wouldn't pass. But we know this, that just one of these is one period of tangent. And guess what? That's good enough for its inverse, right? If I were just to restrict it to one period, it will pass the horizontal line test. Okay, so that's what we're gonna do. So I'll outline it in green. So we're just gonna pick one period length between one set of asymptotes as my inverse. Okay, so over here, which this is a cool looking graph. There's the graph for the inverse of tangent. I'll put that right here. Kind of looks like a logistic graph. Remember those population graphs that we did in algebra? It goes up to its asymptote. It doesn't quite cross that maximum value, that threshold, but it gets closer to that. Okay, so let's list some facts on this board, and then we're going to use these to solve some problems. Okay, so let's go ahead. So let's do cosine. So here's the restricted function, and here's the inverse. Okay, so we're going to put cosine and tangents information here. We already have, I was going to put sine in there, but we already have science information, so we'll just do the other two. Okay, so our restricted was the cosine, okay, and we restricted it from 0 to pi, but we still made sure that our outputs were all covered, so 1 and -1 is still good to go. Okay, inverse. We know what that looks like this. But that's the same thing as if you were, solving for an inverse when you swap out the x and y together. So those are the same implication there if you see that. Arc, cosine, okay, oops. Follows the same pattern. They're equivalent to each other. And we're going to swap the domains and ranges because that's what inverses do. So we get the following. That our x values, what we're plugging into it, is between -1 and 1. And my outputs are going to be some angle value between 0 and pi. And the last one, tangent. There it is. Okay, so its restriction, we did it within its asymptotes. So -pi/2 and pi/2. And the good news is the range, well, we know it just increases and decreases with no limit, so the range is all real values. Symbols, so here's what this looks like. And again, this implies the same thing as x equals tangent of y. Same thing with arc, tangent. And then we'll flip these around for their domains and so forth. So the domain for this guy would be all real numbers instead, and its output will be between -pi/2 and pi/2. Okay. Now, one thing we're going to talk about this. I don't know if it popped in your mind yet or not. We know that there could be angles in other quadrants that we could be using, okay? So when we're saying, like, we're restricting that to just 0 to pi, what about if the angle's in the third quadrant or the fourth quadrant? Like, does that still get computed? Absolutely, and we'll talk about how do we do that. Okay, we're gonna use some reference angles to do that. So it's gonna be very important to know what these are, okay? And how, and what quadrants you're in and so forth. Okay. Let me, yeah. This is good. Okay, we just need exact values. There we go. Okay, so let's try these ones. So let's do the following. Next couple examples. And the logic I applied to the first examples, still the same thing here. Okay, I'm not going to do anything different. So looking at the first one, what I'm trying to do is I'm trying to figure out what's the y value that I get when I do the inverse of cosine with -√3/2. So the first thing I want to do is √3/2. Think about just the first quadrant. What angle gives me √3/2 for cosine? What would that be? Pi/6, right? You okay with that? Okay, so pi/6 gives me this. Now, because it's negative, if you look at the restrictions here, we're going to be in what, first and second quadrant. So if it's negative, we must be in the second quadrant with this. And what would be, since the reference angle is pi over 6, what would be the angle in quadrant 2 with it? It'd be 5 pi over 6, okay? So let's just write this down, just so we know what we did. A lot of time, it's weird, like when you see textbooks, they just spit the answer out. It's like, okay, I get why, but provide some context. So what I'm gonna do is say this. Pi over 6 is when cosine is square root of 3 over 2. We are in quadrant 2, so it'll be 5 pi over 6, okay? So beneath it, I'll put what the answer is going to look like. So if I do the inverse of cosine of negative square root of 3 over 2, it'll be 5 pi over 6. That'll be its output. Okay, let's do tangent next. So this is telling me, okay, what's the output going to be when I plug 1 in to the inverse of tangent? Okay, well, think about it. Tangent is 1 at pi over 4. Okay, and if I look at my range values here, okay, pi over 4 meets it, and it's within that range. So I don't have to worry about what quadrant I'm in. That works perfectly. So let's just note that. So when, well, I'll match the same wording as I did over here. Pi over 4 is when tangent is 1. Since we're positive, we're in quadrant 1, so it's just pi over 4. So let me just write it out fully. The inverse of tangent of 1 is just pi over 4. So knowing your unit circle and knowing what quadrants you're in are going to be very critical for this. Okay, last one. So we're trying to figure out what y is equal to. We take the inverse of tangent of negative square root of 3 over 3. So we know that pi over 6 is when tangent is square root of 3 over 3. Okay? Now, to figure out the negative part, let's go to its outputs here. So this is saying the first and fourth quadrant. Okay, is what we're looking at here. So this must be the fourth quadrant for it to be negative. So therefore, we'll put we are in quadrant 4. So negative pi over 6. So tangent of negative 1 of this guy equal to negative pi over 6. Now, when you solve it yourself, do you have to write little notes? You do not. I like to just put that there so you know what my thought process is, how I'm coming up with it. So maybe when you first start solving it, might not be a bad idea just to write down some breadcrumbs, like how did I get to that answer? It is calculator time. So let's take a look at your calculator. Now, your calculator knows this stuff already, okay? Which is good. It knows that there's some restrictions involved with inverses. It takes that into account, which is perfect. So in this example, we're going to approximate values of inverse functions using a calculator. I'll just abbreviate calculator. I'm out of space. So I have two examples up here. And what we're going to do is figure out the radians and degrees, okay, for both of those values. So in your calculator, let's do radians. And is that great? We'll do those first, and then we'll switch the mode to degrees. Okay, so if you recall, you would have to hit the mode button and make sure radians is highlighted, okay? If it isn't, highlight it yourself by just going down and hitting enter. And then to back out, just hit the second button and mode. It'll go right back to the main screen, okay? So my calculator, oh, it's in degrees, so let me switch it over. Okay, now how do you access the inverse part, right? Like how do you do that? You don't want to hit sign, okay? But if you look above the button sign, you see the inverse in blue. So to access it, you need to hit the blue second button. So hit second and sign, and it'll pop up for you, okay? Now you can type in the ratio, so 8492, okay? And we get that this is approximately 1.0, we'll do 3 places. I didn't really say in the instructions how far to go. We'll do 3 places. Are we okay with that? Did we all get that, hopefully? Okay. Now before I do degrees, it's already in radians. Let's just go ahead and do tangent next. So arctan is the same thing as doing tan to the -1. So hit second and tan to bring it up. And then type in -2.05. Okay. And we get -1.117. Okay. So again, I'm just doing 3 places. The instructions should tell you where to round. Okay, underneath, let's do degrees. So go back to mode, go down and highlight degrees, okay? And the process doesn't change. You're still gonna hit second sign, 0.8492, and your calculator knows that you want degrees, okay? So this should be 58.125 degrees. And then we'll do tangent to finish it. So second of tangent of -2.05. Okay. We get -63.997 degrees. Now remember what the negatives indicate. The negative indicates that we're not going counterclockwise but clockwise. We're going the other direction. So we're looking at, in this case, we'll be in quadrant 4. This case will be quadrant 1, and so forth. Okay. What do you think? We okay with using the calculator? Not too bad, right? And again, we need that because it's not like these values. These are exact values in the unit circle. We know how to find them. These are not on the unit circle, so we have to come up with a way. And again, the calculator actually knows how to do that. All right. Let's transition a little bit. So here's what I want to talk about. I mentioned it already a little bit. What if my value is outside that range, right? Like let's say it's in quadrant 3. Well, the inverse of cosine doesn't go to that point, so how do we use it? Okay, so let's figure out how to do that next. So for this example, again, we're going to use a calculator to approximate the degree measure, and we'll do it to 1 decimal place. So I will give us some direction there. Okay. Or radian measure, we'll do both, so we get practice with it. And we'll say radians up to 4 decimal places. Of the angle theta, okay, subject to the given conditions. Okay? So we'll try that one next. And our example we'll use cosine of theta equals -7/8, and is going to be between 180 degrees and 27. Okay? I'll tell you what, keep it like that. Okay, so I got to solve for theta. Okay, I got to figure out what that looks like. So theta is just going to be the inverse of cosine of that value. Now remember, when you type that in the calculator, it's going to spit out a value here. But if you look at the angle I want, okay, let's put this underneath it. They want quadrant 3. Okay? So we're going to have to do a little bit of manipulation. But first, your calculator. Okay? So let's go ahead. So inverse of cosine of -7/8. Okay? Now the good news is we're in degree mode already, and that's what we are in. So awesome. Let's type it in. So second of cosine, -7/8. Okay, and we're gonna do 1 decimal place, so we do get this to be roughly 151 degrees. Okay, just makes it easier to calculate. Now let me draw a quick picture. So was it 151? So I don't know. There we go. Something like that, but just to have a visual so we know what we're doing. So again, I want to go to quadrant 3, okay? But I don't want to mess up the value of cosine at all. So is there a value in quadrant 3 that we can use that still gives me the same result? Absolutely, okay? So here's what we can do. We could find, I'll make this like theta prime. If we find the reference angle, I can use the reference angle and add it to 180 to figure out the angle measurement in quadrant 3 that satisfies this, okay? So I'm out of space, let me put it up here. Okay. So, to find theta prime, yeah, use red. So I will do 180 minus the 151 that we did, okay? And we get 29 degrees. Okay, so my reference angle is 29 degrees. So to go into quadrant 3, where I want to be, okay, so I'll say to get to quadrant 3, we will add 29 and 180 degrees. Okay? So if we do that, we get 209 degrees. Okay? So this is equal to 209 degrees. Now we can check our work, which is really cool. So let me show you how to check it. Okay? So in your calculator, type cosine of 209 degrees. So I'll do that with you. Okay. So if we do that, we get -0.87. We'll do 3 places again. 5. Okay, you get something like that. Now, in your calculator, type in -7 divided by 8. And what do we get? -0.875. So again, we didn't change its value. We just found an angle that was in this quadrant that satisfies it as well. Okay? So does that make sense, what we did there? So again, how do we break out of that restriction that we created? We use a reference angle, okay? And drawing a picture, I think, does help a little bit. At least I think so, just to know, like, how am I gonna get to the next part? If I wanted to go in quadrant 4, okay, that's fine. You would just be going in the, well, do you wanna go in quadrant? Yeah, we can still do that. But you would still find your reference angle, and this time it'd be 360 minus that amount.